Hey everybody, Trey here. Welcome back to another video. Back with another case study today, and we're going to shift gears a little bit from our usual study of significant tornado events, and instead we're going to take a look at the costliest severe thunderstorm event in United States history, and that is the Great Midwest Derecho of August 10th, 2020. This was an incredible event from a meteorological standpoint. As you can see here, almost 1,000 severe wind reports with several significant reports in there, and this was an extremely impactful event for parts of the Midwest, specifically across the central third of Iowa. You can see here from this wind map taken from Bell et al. 2022, and of course, as we always do, I have plenty of resources, research papers, etc. for this event, and I'll put all the links to those in the description below. But this image, this figure from Bell et al. 2022 shows the swath of severe winds really honing in on central to eastern Iowa, specifically the Cedar Rapids area, where they experienced wind gusts of approximately 140 miles an hour. So this was an incredible event, obviously did some pretty impactful had some pretty significant impacts to the infrastructure and the agriculture across the region. You can see from this map here, before and after, you can see the scarring there from these severe winds that were associated with this particular derecho. So, as always, we're going to go through the meteorology behind the event, but first we're going to take a look, since we don't often look at derecho events, we're going to do kind of a crash course on what is a derecho and how they can form, and some of the criteria that a complex of storms need to meet in order to be determined to be a derecho. So we're going to do that and then take a look at the meteorology behind the event and discuss some of the impacts from the event toward the end of the video. So let's go ahead and get started here. As I said, we don't usually cover derechos on the channel here, so I thought it'd be a good idea to give kind of a quick introduction or crash course on what derechos actually are. And so we'll start out by simply defining what a derecho is. And it's basically just a convectively induced windstorm. And they usually the formation of derechos are usually tied to bow echoes. And bow echoes, you may have heard before, are simply complexes of storms that take on a bow-like shape on radar. They kind of have this bowing out in the middle, and we'll discuss why that happens here in a second. And so derechos usually occur when the overall atmospheric wind profile is mostly unidirectional, meaning that the winds don't really change in direction a whole lot as you go up in the atmosphere. And that is in stark contrast to a tornadic supercell type environment, where you need that strong low-level shear. Hodographs really taking on that classic sort of clockwise curvature in the low levels. Instead, derechos tend to rely on a more unidirectional flow, more straight-line hodographs, and as a result, you tend to see these more often in the late spring into the summer months, when that jet stream kind of migrates a little bit farther north. We're left with a big sort of ridge of high pressure across much of the continental U.S., and you get these storm complexes to kind of fire up over top of the ridge. And we'll talk about this more after we go through the process of formation for derechos. So we'll do just that by taking a look at these schematic diagrams here on the left. These are taken from the SPC facts page on derechos here. Of course, as we said, I'm going to put this in the description box below. But this was written by SPC meteorologists, previous SPC meteorologists Steve Corfiti, Jeffrey Evans, and Robert Johns. And so we're going to be referring to the figures from this particular article, which are shown here on the left. And these kind of highlight the process of derecho formation. So as we said, derecho formation is often tied to the formation of a bow echo. And so you first get storms to fire, and they will, as we know, produce a lot of outflow. So that outflow will spread in the direction of the atmospheric flow aloft. As we said, these derecho events tend to favor more unidirectional flow aloft. So if we have a typical event where the flow aloft, in this case here, is going to be more so out of the west, and that will be the same as we go up throughout the entire atmosphere. So you have a complex of storms that fires up, maybe spotty storms here and there that fires up, and they produce outflow. And that outflow is going to spread out in the direction of the atmospheric kind of mean flow aloft. And this is going to yield new storm formation. As we've talked about before, outflow is basically a small scale type of cold front. So as you have your complex of storms back here, it'll push out outflow ahead of it, and warm air on the leading edge of that gust front gets forced upward along it. As we know, the cold front or gust front kind of acts as a wedge of cold air. So air starts to rise up that steep slope of that cold front or gust front, and as a result, you will get storm formation on the leading edge of that gust front. And that's how these complexes of storms will essentially propagate downstream. You'll get new storm formation out ahead along the leading gust front. So that process kind of continues. You will continue to get rain-cooled downdrafts that reinforce the gust front or strengthen that gust front, and this allows it to kind of grow and elongate in the direction of the mean flow. So you'll get more storm development to happen, and that gust front will continue to be reinforced and strengthen and kind of grow in size, and you'll get kind of a growing mesoscale convective complex along that leading edge of the gust front. Now, when this happens, the overall updraft starts to become a little bit tilted. You'll get this kind of conglomeration of storms, and the updrafts as a whole will kind of start to be tilted toward the rear or backside of the overall complex with height. As you can see here in this diagram number 2 here, you can see this updraft starts to take on more of a sort of backwards or rearward tilt as you go up in the atmosphere. And this is a pretty important process for these derecho formations. What happens is you have a cold pool at the surface, but aloft near this thunderstorm anvil, or this conglomeration of thunderstorm anvils, you have a lot of heat release. There's a lot of warm air aloft over top of this cold pool associated with those rain-cooled downdrafts of the ongoing storms. So that cold air is going to be associated with high pressure, and that warm air is aloft, just above that cold pool, is going to be associated with low pressure. Now, we talked about the difference between high and low pressure before. We said that high pressure, you tend to have clockwise circulation around it, and low pressure, you tend to have counterclockwise circulation around it. You don't tend to have that. That is, by definition, what happens with the flow around these particular high and low pressure systems. Well, that's not 100% true because of some effects of friction and other sort of atmospheric impacts. The flow around these systems, actually, you're going to see a general trend of what we just talked about. Around a high pressure system, you're going to see generally clockwise flow. But the winds actually diverge a little bit outward from the center of a high pressure area. So you can see overall that the overall circulation is somewhat more of a clockwise flow, but the winds are actually going to diverge away from the center of high pressure. And it's the exact opposite with an area of low pressure. You're going to have generally sort of counterclockwise flow around the low pressure area, but those winds are going to converge more toward the center of a low pressure system. So you can see here that you generally have that counterclockwise flow or cyclonic flow around the low pressure system, but the winds are generally going to converge toward the center of a low pressure system. So winds tend to diverge toward the center of a high pressure system and tend to converge toward the center of a low pressure system. And that is important here in this derecho formation process. As we said, we have warm air, thanks to that kind of warm air aloft from the latent heat release of those thunderstorm anvils, atop that cold pool aloft. And that creates an area of high pressure near the surface within that cold pool, and a low pressure area aloft. And so the winds at the surface, near that surface high pressure, are going to diverge. They're going to go kind of flow outward in a clockwise direction from the area of high pressure, but from the area of low pressure, they're going to converge inward. And that is a critical process in the formation of what we call a rear inflow jet. This brown or tan arrow here is evidence of a rear inflow jet. And a rear inflow jet is basically when you have that low pressure aloft, that converging flow near the center of that low pressure system just aloft there, that creates a kind of strengthening of the flow in the mid-levels near that center of low pressure, and that is called a rear inflow jet. And as that rear inflow jet strengthens, that kind of pushes the center of the system outward a little bit. So if you have kind of a complex of storms, more so a north-south line, and you start to get that rear inflow jet to occur, what's going to happen is that center of the system is going to start to bow outward, hence the term bow echo. And it's going to start to look more like a bow with time as that rear inflow jet process takes place. So that rear inflow jet is critical for derecho formation, and so that's going to kind of keep this vicious cycle going. You'll continue to get that updraft tilt toward the rear. You'll start to get that you'll continue to get that low pressure atop the high pressure near the surface, and you'll continue to get those converging winds in the mid-levels, that strengthening of the rear inflow jet, and it kind of creates that vicious cycle. So that overall is going to strengthen the cold pool and really start to bow out this system with time as that rear inflow jet strengthens. So that is really the essence of bow echo formation, and these derechos are basically just a long duration version of these bow echoes. And these bow echoes can continue in kind of a steady state fashion. So this kind of, as we said, is kind of a sort of a vicious cycle there, that continuation of the rear inflow jet strengthening, that tilting of the updraft and creating the rear inflow jet gets transferred down through the surface. That rear inflow jet gets transferred down to the surface through convective downdrafts, kind of pushes that strong wind toward the surface, and as at the surface it'll spread out and really start to take on, the convective complex will really start to take on a bow shape as that occurs. And this is kind of a steady state process for a while, and that's how we get derechos, these long-term, long-duration, severe convective wind events. And as long as the kinematics and thermodynamics out ahead of the bow echo are supportive of maintenance of the convective complex, you'll continue to see severe weather and that cycle continue for a pretty long duration of time. So as we know, you can have mesoscale convective systems and squall lines and bow echoes quite often throughout the year. We see quite a bit of these events throughout the year, but derechos themselves are actually fairly rare. And that's because there's a specific set of criteria that a convective complex needs to meet in order to be determined to be a derecho. And we're going to start by looking at this paper here, Johns and Hurt, 1987. This is kind of the foundational work on derechos. And they came up with a specific set of criteria to determine a convective complex to be a derecho or not. We're going to zoom in right in here. And these are the main criteria they came up with. And the most important one is this first one right here, line A there. There must be a concentrated area of convectively induced wind gusts greater than 50 knots or 58 miles an hour, and this swath must extend at least 400 kilometers or 250 miles in length. So you can't have just sporadic reports here and there. It has to be a continuous, concentrated area of convectively induced wind gusts of greater than 58 miles per hour, which constitutes severe wind, and it has to be at least 250 miles long. So as you can see from our storm reports map here on the right from August 10th, 2020, this is going to be our swath right in here, and you can see it definitely fits the bill as far as that criterion goes. Starts here in eastern Nebraska, goes through multiple states, Iowa, Illinois, Indiana, and even into Ohio, so definitely longer than 250 miles, and you can see that it is a continuous swath. That is critical as well. The swath of reports has to have spatial and temporal continuity, and at least some sort of chronological progression. So once again, it can't just be scattered reports here and there. It has to be, for lack of a better term, a swath of reports, continuous in space and time. You can't just have a complex start, produce a few wind reports, then stop for quite a while, and then produce some more. It has to be continuous in time with a chronological progression. And kind of working off of that here, you can't have more than 3 hours elapse between successive severe wind damage reports or events. So you can't have a 58 mile an hour gust here, then have 4 hours or so go by, and then another one happens there. That's not a derecho. You have to have a, as we said, a kind of a continuous stream of severe wind reports with no more than 3 hours in between. And this has been tweaked a little bit in subsequent papers as we look at Guastini and Bozart 2016 here at their Table 1. You can see that these are kind of listing the criteria from different papers that have talked about derecho climatology. And so this is the Johns and Hurt 1987 criteria over here on the left. And you can see that this bullet number 3 here, this is their the time elapsed criterion here. And you can see this paper here, Bentley and Mote 1998. They used 2 hours elapsing between successive wind reports. Caniglio and Stensrud 2004 used 2.5 hours between reports. So anywhere between 2 to 3 hours is kind of the time that the limit of time that can elapse between severe wind reports within a derecho producing system. But you can see here that our August 2020 derecho definitely didn't have any issues with that. You can see that continuous swath of severe winds there going all the way through from Nebraska through to Ohio. So no issues there. And The kind of final main criterion is that there must be at least 3 reports of 64 knots or 74 miles per hour separated by at least 40 miles. So you have to have significant severe wind gusts, which is the 74 mile per hour criterion, at least 40 miles apart from each other within the swath of overall severe wind reports from a derecho producing system. And so you can see that fits the bill here as well for our August 2020 derecho. These black squares are significant wind reports, and you can see we have several of those along the path of this system. We'll go into the overall distribution of the wind gusts within the swath of severe winds from the August 2020 derecho in a little bit. So you can see that this particular system, August 2020, had no problems meeting these criteria for a derecho producing system. All right, let's take a look at the typical environments and environmental parameters that occur with these derecho events. And Johns and Hurt in 1987 determined that the majority of these derecho events occur with westerly or northwesterly flow aloft. And we talked about that at the beginning of the video. A very common occurrence for this northwesterly flow type event is when you have this sort of ring of fire type of setup. You have that jet stream that typically brings those severe weather setups to the central and southern plains during, March, April, May, early June. That jet stream starts to migrate to the north a little bit during the late spring and into the summer months. So you have this replacement of that kind of active pattern with this anticyclone or large ridge of high pressure that takes up the southern half or 2/3 of the country. But over top of that, you still have that jet stream producing troughs and low pressure systems, and you can have some sort of enhanced flow and then little perturbations rounding the peak of that ridge, and you can get these northwest flow severe weather setups in kind of at the top of the ridge. We call that colloquially the sort of ring of fire setup, and this can take on multiple iterations, this northwest flow type event. These are additional figures from Johns 1984 here. You can have somewhat of a modified version of that ring of fire setup, still a strong anticyclone, but you have a low pressure system that has dug quite a bit and suppressed that ridge a little bit. You can get severe weather in kind of northwesterly or northwest flow out ahead of that cyclonic perturbation there. You can also have a broad cyclonic flow pattern where you have just a very high amplitude trough centered up north, but digs down deeply into the U.S., and you can get severe weather on the backside relative to the axis of the trough there in that northwest flow regime, and so on and so forth. You can have multiple iterations of this type of northwest flow setup. We can also have multiple types of surface patterns with these northwest flow events. These are some more figures from Johns 1984 showing potential surface pattern for these northwest flow events. You can see A here, low up into Canada, trailing cold front, severe weather on right out ahead of the cold front. You can have these northwest flow setups around to the rear of the cold front / stationary front, and so on and so forth. Multiple iterations of these upper air and surface patterns that can come together to create a northwest flow severe weather event and potentially a derecho event. Now, as far as parameters go, we can look at this paper from Evans and Doswell 2001. They did some study on these derecho events and some of the overall parameters, typical parameters we see with severe weather events, and they did some of these box and whisker plots for derecho events. So let's scroll down here to this particular figure. We'll start with mixed layer CAPE. I want you to look at this box down in here. So this one on the left is going to be for all derecho events. And again, we're looking at mixed layer CAPE. And you can see we have a pretty wide range of instability values, with most centered between this kind of 1,100 joules per kilogram to about 3,000 joules per kilogram. That's where most of these derecho events fall into. But we can also have these events occur with pretty extreme CAPE, over 5,000 joules per kilogram. So generally these derecho events occur with moderate to strong instability. As far as kinematics go, as far as wind shear goes, we'll scroll back up here, and we can see the 0 to 6 kilometer shear values associated with these derechos. And this is in meters per second, and the conversion between meters per second and knots, our typical value or unit for wind shear, you can just multiply these values by about 2 to get our value in knots. And you can see that the wind shear is quite a bit less than a typical sort of supercell event. Still kind of in the range, definitely in the range for severe weather. You can see anywhere from about 22 knots to about 40 knots there. So kind of straddles that line between more multi-cell severe convection and supercellular convection there. We can have derecho events occur with strong shear. You can see up to about 36 knots there, 36 meters per second, 72 knots. And we can also have these events occur in very weak shear environments. So generally, these derecho events occur in sort of moderate to strong shear, moderate to strong instability, CAPE environments, and sort of weak to modest or adequate, if you will, shear type environments, at least for deep layer shear values. And as we said before, these derecho events often tend to favor more unidirectional wind profiles with height. And these are some composite photographs calculated in the Bentley et al. 2000 paper, again, link in the description below. This is for the initiation zone of the southeastward moving severe weather, or derechos, so the northwest flow derechos. And this is for the downstream environment. You can see these photographs are fairly straight as they go up into the atmosphere. You can see maybe a little low-level shear, especially in the downstream photograph there, but mostly these photographs are fairly straight, representing a more unidirectional wind profile with height. One more thing to wrap up this primer on derechos. We can have two different types of derechos. We can have one that's called a progressive derecho, and we can also have a serial derecho. And a progressive derecho, which is denoted by the drawing on the screen here, this is from Johns and Hurt 1987. A progressive derecho occurs when you have a single bow echo producing the severe wind damage, severe wind reports, and it moves perpendicular to the direction of the mean flow. You can also have a serial derecho, which is the schematic diagram here. That is when you have sort of these embedded bow echoes within a larger sort of complex of storms. And these serial derechos move parallel, very parallel to the direction of the mean flow throughout the atmosphere. And often these serial derechos will occur out ahead of a stronger surface low, whereas the progressive derechos are more of your northwest, kind of classic northwest flow events, moving generally along a stationary front. That tends to be key with these type of progressive derecho events. And we'll talk about which type the August 2020 derecho was here coming up in just a little bit. So now that we've talked about what derechos are and how they work, let's go ahead and dive into our case study of the August 10th, 2020 derecho. Now, just a subjective note before we start. I find that derechos are not quite as interesting or maybe as fruitful a study as a tornadic supercell case study. If you've been a supporter of the channel for a while, you've probably seen some of the case study videos such as El Reno and Greensburg. Those tornadic supercells have very intricate details about them. Lots of behaviors within the storm that we can study and that impact what we see at the ground. And the meteorology behind those events, there's a lot of different nuances that help those events go from a normal severe weather event to a high-end, upper echelon severe weather event. Derecho events and MCS events in general, on the other hand, just are not quite as interesting. As we talked about briefly in our derecho primer, the overall environments for these types of setups, you basically need moderate to strong instability, less wind shear, and that is pretty much what we see on a frequent basis across the United States for most of the late spring into the summer months. Again, we see that ridge start to build in across much of the country. That jet stream migrates a little bit farther north. So a lot of days we have strong instability, weaker deep layer shear, especially weaker low-level shear. And so, as you might guess, these derecho events are fairly tough to actually forecast. And for example, our August 10th, 2020 derecho, this is the day 3 outlook from the SPC issued on August 8th, 2020. You'll notice here we have a marginal risk from Kansas up into southern Iowa, northern Missouri, into Illinois and the Great Lakes region. Our area of interest, most of the track, at least the early portion of the track of the MCS, not even in a severe weather risk. So you can see that these can be fairly difficult to forecast. And again, these derecho events or MCS events are not quite as interesting from a storm behavior perspective and maybe a meteorology perspective as a tornadic supercell or tornado outbreak type event. But we're going to do our best to go over the meteorology behind this event and talk about why perhaps this particular event was so impactful and so strong. So once again, we start off here with our day 3 outlook, and this was somewhat tough to forecast. As we said, the SPC did not even have a severe weather risk for most of that early portion of the MCS track. We move on to day 2, much of the same until late in the day. They add a slight risk down here into Kansas and Missouri. Still, they actually take out the general thunderstorm risk for most of southern or South Dakota into northeast Nebraska. But by late night into the morning hours on the morning of August 10th, that is when we started to see a much higher risk for severe weather across this corridor, and eventually was upgraded to a moderate risk by 1630Z as it became apparent that this derecho was going to be a significant one. All right, let's dive into the meteorology behind this event. We'll start off at 500 millibars at 0Z on August 10th. So this will be the evening of the 9th, going through the morning and afternoon hours on August 10th. And you'll notice right away, we have kind of this zonal flow pattern across much of the United States as part of this broad, elongated ridge of high pressure, centered across the southern 2/3 of the U.S., more or less. But the amplitude of this ridge has been suppressed a little bit by this trough digging down from Canada into the northern plains. And we'll see some height falls here across this region as we go through the loop here. Keep an eye on this 5820 geopotential height contour. This is going to drop a little bit south with time as we go through this loop, and you'll see that right here. And so we have some height falls ongoing, and those height falls help to initiate rising motion, and this is going to be our main initiation mechanism for storms in this particular environment. So this 500 millibar trough, this little shortwave embedded within the flow, is helping to suppress the ridge and initiate storms here out across southern South Dakota during the early morning hours of the 10th. And this is pretty similar to our figure 8 here from John's 1984, this figure on the left. And this was probably the closest of his northwest flow severe weather event 500 millibar setups. This one here on the left, figure 8, kind of this broad ridge out across the southern U.S. with this Canadian low at 500 millibars, this trough dipping down over top of the high pressure ridge, creating some westerly or northwesterly flow out ahead of the trough, and an enhanced area of height falls and rising motion out ahead of the trough, rounding the top of this elongated ridge. So closely matches this northwest flow 500 millibar setup from John's 1984. Now let's go straight down to the surface. Normally we take a look from the top down level by level, but let's go straight to the surface, because really the 500 millibar pattern, the overall background flow, and the surface pattern are really, really important for these derecho events. So let's decipher what we can see here at the surface. So we'll start here at 6Z on August 10th. So right before storm initiation across southern South Dakota. We're centered here on Iowa, of course. And so you'll see right away a fairly broad area of 70s dew points out here across Nebraska into Iowa, down toward Kansas and Missouri into Illinois. But you'll see this wind shift as well. We have northerly winds out across South Dakota into northern Nebraska, switching to southeasterly winds out across Nebraska into Iowa. So definitely a cold front stretching down from a low located somewhere up into Canada. And of course this map is cut off, but the low is all the way up here into Canada. And actually storms initiated back in here. You can see there's a little bit of kind of wraparound moisture here. Even though the winds are northerly, we still have some decent moisture making its way behind this cold front. 65, 72 dew point, upper 50s dew points up into southeast South Dakota. So there is some moisture for that trough to work with as it moves through here. So storms were able to initiate out across this region in a decently favorable environment, at least thermodynamically, for storms behind the cold front. And as again, we'll refer back to John's 1984, and we'll go up to his surface map cases. And again, this was fairly close to, we said this was kind of a match between A and B. So A here, low up into Canada, cold front draped down to the southwest, area of interest right out ahead of the cold front. And that's going to kind of be what this event shifts into, but it starts off here not so much with this ridge of high pressure all the way behind this cold front, but these storms are going to fire behind the cold front and eventually catch up to the cold front. We'll talk about that as well in the coming minutes here, and that may have been a reason why this event was able to start really ramping up across Iowa. Now we saw from our Johns and Hurt 1987 schematics on progressive and serial derechos that some sort of stationary front is often in play to help with the initiation of these derecho producing systems. And we can see here from this Bentley et al. 2000 figure that here's a schematic diagram of a typical setup of the derechos that they studied in their paper. And you see a stationary front here, and generally moisture pooling along it, or advection of that moisture north of the front can help initiate those the eventual derecho producing MCS. Now we'll go back to our surface map here and try to pinpoint if we can see any sort of stationary front out in here. So our cold front, located somewhere in this vicinity, you see that wind shift right there, northerly winds shifting to southeasterly winds here across Nebraska. Now I've been trying to really focus here on the Nebraska-Iowa vicinity, and I really don't see anything indicative of any sort of stationary front here. Any sort of boundary in this vicinity to really help pool that moisture and allow the derecho to kind of track along it. Not really seeing that at all here. So that may be a slight difference here, at least at the surface, from a typical derecho event. You see as we go on with time as well, still really don't see anything across Iowa. This is 11Z, so as the storms were getting going, approaching the Iowa border, still not really seeing much of anything out here across this vicinity into Iowa. Now, if we go back to our meso analysis, let's go back and look at frontogenesis in the 850 to 700 millibar layer. So we're going to go up a little bit in the atmosphere. And again, this is called frontogenesis. And frontogenesis is just a fancy word for the increase in the horizontal thermal gradient. So we know that a frontal zone is basically a gradient in temperature. For example, a cold front or a warm front is going to have warm air moving into a region of cold air. There's a temperature gradient along this frontal boundary. And frontogenesis is, again, a fancy word for saying the increase in the horizontal thermal gradient. So anywhere where we may see the initiation of a frontal boundary. And you can see here it's from the 850 to 700 millibar layer, we do have a frontogenesis bullseye right here across southeast South Dakota, right in the vicinity of where those storms fired. This is at 6Z on August 10th. So right before storm initiation, we see this frontogenesis bullseye. So there may be some sort of thermal gradient trying to tighten up here aloft behind the surface cold front, which again is somewhere out in this vicinity, to help initiate those storms out across southeast South Dakota. So maybe not seeing much of a surface reflection of any sort of boundary, but we do see a little bit of a frontogenetic response here aloft across southeast South Dakota. So something to note there. But overall, the general 500 millibar pattern and the surface pattern are fairly favorable, fairly common patterns in these derecho type setups. Let's go now to 850 millibars, and so we'll look at our low-level characteristics. And once again, we don't, in the summer, usually have those deep digging troughs down here in the plains that would traverse the Rockies. You get sinking air on the lee side of the Rockies and eventual surface low development, or lee cyclogenesis, to the east of the Rockies. That trough up here is up here way up to the north into Canada, into the far northern plains. So we're not really seeing a very stout response as far as the low-level jet goes. And that is typical for these types of events. We're into summer, not really a lee cyclogenesis response, that low-level jet not really in place. We do maybe have just broad, ever so slight sort of cyclonic flow here out across the central high plains. We go back a few. You can see this kind of closed contour here, very broad, weak cyclonic flow there, maybe across Colorado into Wyoming, but really nothing that's going to elicit a very significant mass response out in here across the central high plains that would help initiate a strong low-level jet. So low-level shear should remain weak out across this region because of this very weak low-level response. And so that is fairly favorable, fairly typical for what we see with these derecho events. This is from Guastini and Bozart, 2016. Composite 850 millibar pattern for these derecho events here. And you can see very similar setup here with this composite map in their study. Maybe very broad sort of troughiness or weak cyclonic circulation there across the central to northern high plains. Flow at 850 millibars, very weak and out of the south or south-southwest. And we have kind of this gradient setting up out here in this theta E, equivalent potential temperature, the juiciness of the air. We have a gradient in that just out ahead of the surface or the low-level weak trough there. And that's exactly what we're seeing with this particular event. So storms started to fire out here across southern or southeastern South Dakota right around 2 a.m. or so, Central Daylight Time, about 7Z. You can see we get storms to kind of increase in intensity there, right around 7 to 8Z. Some strong to severe storms out here across southern South Dakota moving into Nebraska. These storms actually started producing some large hail early on. Here is a photo of that large hail from Gregory, South Dakota. Some pretty decent sized hail in this, and that's not often something we talk about with a squall line or MCS type event. Usually it's more of a damaging wind and embedded tornado threat, but actually the storms initially produced some large hail, and we'll take a look at some soundings to kind of give us the reason why. Here's the 12Z sounding from the RAP model for Sioux City, Iowa. So right out ahead of this line, as it started to get organized and move into the kind of toward the South Dakota-Iowa border region. So right away we see a pretty significant inversion there, between about 700 and 850 millibars. Again, this is going to be behind the cold front, as we talked about on our surface analysis, behind the cold front, and so these storms were definitely elevated in the cooler air to the northwest of the frontal boundary. So that's why we see this pretty stout inversion there. So that is going to do a couple of different things. That is going to, number one, negate any tornado threat that might happen. Not that the low-level shear is even strong enough for tornadoes, although we did see a few tornadoes later on with this system as it moved into Iowa and Illinois. But what it's also going to do is it's going to kind of put a lid on the atmosphere and prohibit any strong gusts from getting down to the surface. Just like a tornadic circulation isn't able to really penetrate and drill through this stable layer in the low levels, the downdrafts of these storms and any really strong winds created by these downdrafts are unable to reach the surface, at least fully, because of this strong stable layer near the surface. So that's perhaps why we start off with a fairly tame-looking cluster or complex of storms, and then later on, as we'll talk about, this inversion eroded quite a bit fully and allowed those strong gusts to get to the surface. But as far as a hail perspective, you can see very steep lapse rates aloft here, a layer of very, very steep lapse rates here in this layer from between about 500 and 700 millibars, an average lapse rate or a maximum lapse rate of 9 degrees Celsius per kilometer. And you can see some pretty high numbers here as well. The 3 to 6 kilometer lapse rate, 8.4 degrees Celsius per kilometer. So very strong, very steep lapse rates in the mid-levels of the atmosphere, leading to some pretty strong instability, at least early on here. Elevated instability, though, as we said. But this is going to be enough for some hail production in these storms. Deep layer shear on the margins, but strong enough for some more robust updrafts. And we have some pretty significant instability in that hail growth layer within these storms. So that's why we saw some large hail early on with these storms. The Omaha observed sounding shows much of the same. This is the 12Z Omaha, Nebraska sounding. Again, stout inversion in the low levels behind that front. Lots of elevated instability here, and that allowed for that significant hail production in those storms. You can see those extremely steep lapse rates there in the mid-levels. And that's going to play a role later with the damaging wind threat as well. So the complex continued to intensify and organize as it moved toward the Nebraska, Iowa, South Dakota triple point area. And as it moved into Iowa, that's when we started to see some of the wind reports start coming in. We actually had a combination of some wind and hail in far western Iowa near the town of Breda. You can see here from this image from Bell et al. 2022, some wind-driven hail damage here in some of the crop fields just outside of town there. You can see kind of the streakiness in those fields there within that brown patch, evidence of some wind-driven hail. So the hail threat would subside after this point. We'd transition to more of a damaging wind and an embedded tornado threat, mostly a damaging wind threat. Obviously, as the complex continued to intensify and organize into more of a solid squall line / MCS, the damaging wind threat took over as well. Now let's go back to our surface maps and kind of show what was happening at the surface with respect to the location of the cold front and the MCS. So as we talked about, we'll go back to 6Z here, our cold front here somewhere in this sort of wind shift area from southwest Minnesota into northeast Nebraska, somewhere in there. And of course, it's going to move off slowly to the east or southeast with time. And keep an eye on that area as we go through with time. So let's stop it at 13Z here. So you can see that the cold front started out there, now somewhere across kind of central to southwest Iowa into southeast Nebraska, right in there. Now here's our MCS. You can see the thunderstorm icon right in there. So our MCS back in here still. So we're still well behind the cold front. But watch what happens over the next couple of hours. The cold front not moving all that fast. By 14Z, our MCS is somewhere in this vicinity. Our cold front, again, hadn't moved quite a lot in that time frame. Somewhere in here looks to be our cold frontal position. So the MCS kind of catching up with the cold front as we progress through the morning hours. And by 16Z, let's take a look at the location of the front. So the front, here's our wind shift somewhere in this vicinity, right in here. I put it kind of right in there. And our MCS right over the Des Moines area. You can see those thunderstorm icons there, right over there. So that by about late morning, mid to late morning or so, the MCS had actually caught up to the cold front. And so now we were talking about an environment that was destabilized fully out ahead. And so let's take a look at the downstream environment and how that progressed through the morning. So this is going to be a series of RAP model soundings starting at 10Z, going to 17Z at Cedar Rapids, Iowa. As we talked about, Cedar Rapids kind of took the brunt of the strongest winds from this derecho producing system. Some wind gusts near town registered about 140 miles per hour, which is just crazy to think about from a straight line wind event. So we're going to go through again a succession of soundings here starting at 10Z to about 17Z, right up before the time that the area was impacted by the system. So we start at 10Z, and of course, surface heating had not commenced yet. We were still in the dark. So we still had this inversion to deal with in the sort of open warm sector, you could call it. Still quite a bit of instability, elevated instability though, with some steep lapse rates there in the mid-levels of the atmosphere. So indicative of a nice elevated environment for some hailers, as we saw back out in western Iowa. But watch what happens as we go through with time. As we go toward 15, 16, 17Z, notice what happened to this inversion. You still see it a little bit here, but we are not quite capped anymore. Mixed layer SIN had dropped to about minus 18 joules per kilogram, which effectively is negligible. So for all intents and purposes, we can say that we were pretty much completely destabilized here at Cedar Rapids by about 17Z or so. And that was a similar environment was taking place across central Iowa, as well as the MCS was moving across the central portions of Iowa. So what happens is this inversion had diminished almost completely, and that wouldn't then allow those strong winds from that developing rear inflow jet to actually penetrate to the surface. And that's how we started getting the strongest wind reports across central Iowa into eastern Iowa towards Cedar Rapids, is because we were now fully destabilized. We can also see a similar process taking place in the observed soundings out ahead of the bow echo. This is at Davenport, Iowa at 12Z. So the early morning sounding balloon showing a moderately unstable environment, capped low levels, as we saw at the Cedar Rapids site. Watch what happens by 17Z though. We increase that instability throughout the entire atmosphere and significantly decrease that low level convective inhibition. And so that was why those gusts were able to reach the surface. We can go even farther down into Illinois as well. Very similar setup there, modestly to moderately unstable there in Lincoln, Illinois at 12Z, and by 17Z, much of the same. Strong increase in instability and a strong decrease in the low-level inhibition there out ahead of this bow echo. And that's why we saw that swath of wind start to take shape across kind of central to eastern Iowa and kind of maximize itself over eastern Iowa. As by that time, we were pretty much fully destabilized, and we were able to get those strong winds from the rear inflow jet down to the surface. Now let's talk about that rear inflow jet. We're going to zoom in on the radar from the Davenport radar site, the Quad Cities radar site, and we'll take a look at how it progressed through the Cedar Rapids area. So this is reflectivity. Cedar Rapids is going to be right in there. And you can see by 17Z or so, we had a very well-defined bow echo. You can already see that bow shape there on radar, indicating those winds were really starting to, that rear inflow jet was really starting to push and accelerate that gust front outward in the center of that bow. So we go through with time, very strong bow echo. You can see it impacts Cedar Rapids right about now, maintains its structure, very impressive structure. Comma head, classic kind of comma head shape there with this bow echo, and the strongest winds were just located off to the south of the kind of comma head right there, just north of town. Now let's take a look at the velocity data. This is some pretty impressive velocity data. So as I've said before, this is unfortunately not de-aliased. So this is going to show some folding, but we can still decipher some of the winds within this radar data here from this site. So we go on with time. This is when it's impacting Cedar Rapids, and you can see a broad swath of strong winds right at the apex of that bow. The reflectivity would show that the bow echo apex was kind of right in this vicinity. So as we know from Doppler velocity data, inbounds are green, means they're going toward the radar, and outbounds are red, means they're going away from the radar. Well, this area right here of reds is not actually going away from the radar. The radar site's right here. The MCS is pushing this way. So those winds associated with the bow echo are as well. That means that this area of winds has been folded or aliased, and I'll explain aliasing real quick. Every weather radar has a maximum velocity that it can read. In this particular case, this WSR 88D at Davenport, its maximum is 70 knots. You can see the edge of the scale is at 70 for outbounds, 70 for inbounds. So this area, which should be green, means that it has exceeded that 70 knot threshold. So that means it goes up the scale, and when it reaches that threshold, it goes all the way to the other end of the scale. And so this area of reds is greater than 70 miles an hour. This area in particular has gone back to green, which means it has gone through, hit that threshold, folded back to the other end of the scale, has continued to go up the outbound scale, and has now dipped back into the inbounds once again. So that would mean that this is at least 70 knots, plus another, we'll say about 20 knots or so. That's 160 knot winds. Not terribly far off the surface. Radar site is here, not horribly far off the surface. We're still quite a ways from that radar site, but maybe a couple thousand feet off the surface. That's 160 knot winds. That translates to 184 miles per hour. So these winds right in here, right about 180, 190 miles per hour, a few thousand feet off the surface. Of course, that not reaching the surface, but just shows you that we had an extremely strong rear inflow jet associated with this bow echo, and as a result of the path from aloft to the surface being kind of cleared as that cap eroded, those gusts were able to make it to the surface in some semblance of the 120, 130, 140 mile an hour range there in the Cedar Rapids area. So just a pretty impressive radar data associated with this system, and that would continue as it pushed its way into eastern Iowa and into Illinois. You can see we still have that area of multiple folds there within that stronger area of winds. So very, very strong rear inflow jet associated with this particular system. And the potential for significant damaging winds reaching the surface in this particular event was expressed pretty well by a quantity we call downdraft CAPE, or DCAPE. And all DCAPE is the maximum energy available to a descending air parcel, usually in the form of a downdraft. So it's basically the opposite of regular CAPE. Regular CAPE tells us how buoyant the atmosphere is, how able that air is to rise. Whereas downdraft CAPE, that's the energy of a parcel that is descending. And the more DCAPE you have, the higher the potential for significant downdrafts that might produce damaging winds. So you can see here as we go on through time, this is a map from SPC mesoanalysis of DCAPE. And a general rule of thumb for DCAPE is anything over 1,000 joules per kilogram. That's kind of your threshold for an increasing threat for significant damaging winds reaching the surface via downdrafts. So we go through with time here, and you can see that we have a pretty large reservoir of very strong downdraft CAPE out ahead of this particular MCS. Pretty much widespread, 16 to 17, 1,800 here across much of eastern Nebraska, into Iowa, about 13, 14, 1,500 out in here. So very strong reservoir of DCAPE out in front of this particular environment. And the way you find downdraft CAPE, we'll take an example here from our Davenport 17Z sounding. The way you compute downdraft CAPE from a sounding is you first find the lifted condensation level at 700 millibars. If you're unfamiliar with what a lifted condensation level is and how to find it, head back to my definitive guide to skew-t's and photographs series. I'll put a link to that in the description box below. So our first step to find DCAPE using a sounding is to find the LCL from 700 millibars. So we start, just as a refresher, we start by going up along the dry adiabat from the temperature at our level of interest, and we go up from the dew point along the mixing ratio line at our temperature of interest. And where those two meet, that is our lifted condensation level. In this case, that would be right there for our 700 millibar parcel. Then we follow the moist adiabat down to the surface, and the area between that parcel trace and our atmospheric temperature profile is our DCAPE. So you can see we have quite a bit of downdraft CAPE there, and in this case we have a DCAPE here at Davenport at 17Z of over 1,300 joules per kilogram. That's very, very high, and you can even see as we go farther east into Illinois, our DCAPE value is over 1,600 joules per kilogram. That is definitely on the high end as far as derecho environments go. If we take a look at our Evans and Doswell 2001 paper, here was a box and whisker plot for downdraft CAPE for these derecho cases. And you can see where our values fall here. Definitely on the upper end of the spectrum here. This is kind of our middle value, our median value, centered around that 50th percentile. You can see that 1633 value is definitely well into the upper echelon for our derecho cases. And you might be able to see from our discussion here what might be able to increase the DCAPE value. Steep lapse rates definitely can do that. You'd like to see those steep lapse rates there in the low to mid levels, as that will kind of really tilt that atmospheric temperature profile and give you kind of a lot of space in between your parcel trace and your environmental temperature profile. Dry air aloft can also increase downdraft CAPE. Dry air gets entrained into thunderstorms and can really enhance the downdraft potential through evaporational cooling. So those are a couple of ways that you can maximize downdraft CAPE here. And you can see we have a little bit of dry air through the environment, so that definitely added to it. But the steep lapse rates here in the low to mid levels definitely aided in increasing those DCAPE values across the region. So the threat for significant downdrafts and significant damaging winds from those downdrafts was extremely high in the environment out ahead of the MCS, and you can see from our radar data that we definitely were able to get some very, very strong winds to reach the surface, and DCAPE forecast that pretty well. So the derecho continued off into eastern Iowa, into Illinois, and even through Indiana, into far western Ohio. So we know this derecho was notable for its intensity, but also its longevity. And I want to touch on the longevity here. You can see from this radar data that it just keeps going, keeps that classic bow echo shape, strong, very strong winds there into eastern Iowa and through Illinois, impacted the Chicago metro area, and just continued to produce damaging winds and significant damaging winds at that, as well as a few tornadoes as it moved on in through Indiana and Ohio. So multiple states this derecho traversed before it finally lost some steam as it went into Ohio. And we can take a look at the mixed layer CAPE analysis, and just to kind of put this in perspective, this is where things started. Southeast South Dakota, this was kind of the edge of the sort of CAPE axis instability reservoir there. And we know that, of course, with some surface heating, we got that instability to increase here with eastern extent as well. And so I am going to go forward in time here and kind of denoting the western edge, or the eastern edge of this kind of instability reservoir. We'll call it right in there in through Ohio. That is a full 3 states, and we'll call it a few parts of some other states. So, essentially a 4-state-wide axis for this derecho to feed off of, a favorable ingredients for this derecho to feed off of. That is pretty incredible. A typical warm sector across the southern plains or southeast might look something like this. Maybe half a state wide, maybe a state wide at most. To have an instability in a reservoir of favorable ingredients for a storm system to feed off of for a 4 to 5 state wide distance, that's pretty incredible, and that's going to create a favorable environment for a derecho to maintain itself for quite a long time. As we said in our derecho crash course, that cycle continues, that rear inflow jet creation and maintenance, helping those downdrafts get to the surface and helping to intensify that cold pool. That's a vicious cycle that continues to take place as long as the kinematics and thermodynamics are favorable. And you can see we had a very, very long stretch where those thermodynamics were favorable for this particular storm system. And we can take a look at some soundings here. We'll take a look at 21Z. This is Gary, Indiana. So moving in east of where this derecho kind of maximized itself across eastern Iowa into Illinois. This is farther into Indiana. Gary, Indiana, you can see a very similar environment, very strong instability, almost 4,000 joules per kilogram of mixed layer CAPE, fully destabilized atmosphere there. Very sort of weakish low-level shear with strong kind of deep layer, strong to modest to moderate deep layer shear there. So that environment was definitely favorable. We'll continue into Fort Wayne, Indiana, even farther east, still a favorable environment, 3,000 joules per kilogram of CAPE, very strong low-level instability as well, very much the same. And you can see by western Ohio, that's when we started to finally see a drop-off in the overall favorability of the ingredients for this event. You can see the Findlay, Ohio sounding here from the RAP at 1Z. You start to see that instability drop off a little bit, under 1,000 joules per kilogram of mixed layer CAPE. So finally, by the time this thing reached western Ohio, it's when it started to lose steam because it was kind of running out of that favorable sector of ingredients for it to work off of. So the longevity definitely was of interest with this particular event. Whereas a typical severe weather event, you might see a kind of confined warm sector. Not the case for this one. A very, very wide warm sector, evidenced here in our mixed layer CAPE fields, and our overall field of favorable ingredients extended at least 3 to even 4 states wide at times. So no surprise that this thing was able to maintain itself for quite a while and produce intense winds given the overall favorability of the ingredients. Speaking to that, let's put the ingredients for this event into context. We'll look at our Cedar Rapids 17Z RAP sounding here, our proximity sounding, just before the derecho reached its max intensity. So we'll look as well at our Evans and Doswell 2001 paper, and we'll look at shear, mixed layer CAPE, and DCAPE for this particular Cedar Rapids sounding. So we'll start off with 0 to 6 kilometers shear, about 30 knots or so. And that kind of puts it right in the middle of this range, this typical range for derecho environments. Again, this is in meters per second. You can kind of multiply by 2 to get our value in knots. So about 15 meters per second, about 30 knots or so. That's kind of right squarely in that middle range, what we typically see for derecho environments. We'll scroll down to our mixed layer CAPE box and whisker plot here on the left. And of course, as we talked about, the instability was fairly strong with this event. Cedar Rapids sounding here showing about 3,500 joules per kilogram of mixed layer CAPE. And as we see from our box and whisker plot here, that is definitely above the range that is typical for derecho. So very strong instability, stronger than what most derechos tend to have. Definitely on the higher side there. As far as DCAPE goes, we'll take a look at that. We already talked about that as well. Cedar Rapids sounding showing about 1,250 joules per kilogram of DCAPE. That puts it just above that typical range for DCAPE for derechos, and we saw some other examples within this environment of even stronger downdraft CAPE, 1,600 joules per kilogram or so there as well. So definitely on the upper echelon for that as well. We can also compare our wind profile to what was seen in Bentley et al. 2000. This is our Davenport 17Z sounding, might be a little bit more representative of a wind profile as far as the downstream environment goes. You can see modest low-level shear, modest deep layer shear, and that's very similar to what we saw in the downstream environment composite photograph in the Bentley et al. Paper. Weakish low-level shear, modest to moderate deep layer shear, so a very similar sort of environment. Once again, not your classic, very curved, sickle-shaped, meat hook-looking photographs as you might see for a tornadic supercell event, but muted, low and deep layer shear helps fuel these events, and that's exactly what we had with our downstream environment for the August 2020 derecho. So the takeaway is that this environment, the ingredients for this environment were definitely on the higher side, definitely on the more favorable side for derecho development and maintenance. And when you have those kind of extremely favorable ingredients over a very broad spatial extent, you're going to have the ability for a pretty significant storm system to unleash its wrath for quite a long duration. And that's exactly what we got here. Before we wrap this case study up, I wanted to do just a brief satellite breakdown of this particular event. We'll use our imagery from the GOES satellite using a combination of infrared and visible satellite imagery. The infrared portion is this colored portion right here, and that tells us the temperature of the cloud tops that the satellite is seeing. And the warmer the colors are, the more the reds and the blacks you'll see, those are the colder cloud tops, and that means very strong updrafts in most cases. So you can see here a very prominent area of enhanced cloud tops, colder cloud tops, overshooting tops there with this system as well, the strongest portion of this complex. And we go through with time, you can see that that area of overshooting tops and very cold cloud tops stays right about in line with where the strongest winds are located. We come up on the Des Moines area, there's our area of overshooting tops and very cold cloud tops, and we continue with time, and you see that is the case there as we go toward the Cedar Rapids area as well. Very large area of colder cloud tops and overshooting tops there near where the strongest winds occurred in Cedar Rapids. We can actually go to our paper from Bell et al. 2022. This is kind of a closer image of the infrared satellite imagery here on the right as the storm was over Cedar Rapids, and you can see a very broad area of extremely cold cloud tops right where at the apex of that bow right there that was moving through town where the strongest winds were located. So these storms were very, very potent, very explosive thunderstorm development in a highly unstable environment, led to very tall storms as well, able to reach high in the atmosphere, and those cloud tops were very, very cold, indicating very explosive convection. One more thing you can see as we go through with time, I'm going to back it up a little bit here. And it's a little tough to see, but if we go through this kind of fast, you can see kind of these ripples emanating out from this center of cold cloud tops here. We talked about this in the Gerald, Texas tornado case. These are called gravity waves. And gravity waves are just like if you were to throw a rock into a still pond. They're going to create ripples. That is the same as a strong thunderstorm complex, a very explosive thunderstorm complex, really punching up into the upper portion of the atmosphere toward the tropopause, into the stratosphere. And that explosive updraft, those explosive updrafts kind of cause ripples in that environment. Those are called gravity waves, and those can emanate out and be indicative of a strong MCS, a strong derecho, and derecho producing system, and we saw that with this particular system. So all signs, both on radar and on satellite, showing a very potent system, and that was no surprise given the both spatial extent of the ingredients and the favorability of those ingredients for this event. And one final note, we haven't yet designated whether this was a progressive or a serial derecho, and you can see by the radar data here, this is a progressive derecho. As we discussed before, it's just one single bow echo doing all the damage. Now it does expand down to the south a little bit in spatial extent, but this was generally a progressive derecho with one main bow echo doing most of the damage. So that's going to wrap things up for this case study. Again, derecho environments might not quite be as intricate and as complex as tornadic supercell environments and behaviors, but I think we did a kind of as complete a job as we could here of trying to decipher the meteorology and the behaviors behind this particular event. Once again, this was the costliest event, a severe thunderstorm event in United States history, with some just really impressive damage reports. Again, Cedar Rapids lost about 65% of its tree canopy with the 140 mile an hour winds there. Lots of damaged crops, as we know, lots of damaged infrastructure. Definitely made a mark on the Midwest, and you can still see some of those scars today if you travel through this area. So that's going to do it for this case study. Thanks for watching, and we'll see you in the next video.